Last time we talked about electric fields due to continuous charge distributions, and we sort of introduced how we might go about calculating the electric field due to a charged, a continuous charge distribution. We came up with an equation that says the electric field is equal to the integral 1 over 4 pi epsilon naught dq over r squared in the r hat direction. Today we're going to do some examples of how that might work. So the first example is, let's calculate the electric field due to a uniformly charged rod. Let's say that the charge on the rod is equal to, Q is equal to lambda, the charge per unit length, times the length of the rod. Now I want to find what I'm going to do to find the electric field at point P, or at the origin, is to integrate over the length of this rod with respect to point P. The way I'm going to do that is I'm going to substitute immediately. For now, we can say if it's a positive charge, of course, the field at point P will be pointing in this direction, the minus x direction. But so for now, let's not worry about the direction. We know which way it's going to be pointing. Let's just calculate the magnitude. My first inclination is to say integrating dq is going to be a real challenge in this case. Let's not do that. Let's substitute. I can write dq. We'll write that as lambda dx from the x direction. I can write r squared. Let's write r squared. Let's write that as x squared. And I have to integrate over the length of the rod. That is to say, I'm going to integrate from d, because the rod's a distance d from the origin, to d plus L. So I can write this as 1 over 4 pi epsilon naught. I'm going to put the lambda. Lambda is a constant, so I'll pull it outside the integral. dx over x squared from d to d plus L. If I integrate that, I get E is equal to minus lambda over 4 pi epsilon naught x between d and d plus L. So my field then I can write as lambda over 4 pi epsilon naught 1 over d plus L minus 1 over d. Or if I want to combine terms, that can be equal to 1 over 4 pi epsilon naught times the quantity q over d times L plus d, since q is equal to lambda times L. Notice if the charge is very, very far away, if the rod is very, very far away from the origin, the L plus D in the denominator can probably just be written as D, and it looks like a point charge. So for D very large, E is approximately Q over 4 pi epsilon naught D squared, which of course looks like a point charge. Very interesting. Let's now look at the electric field due to a uniform ring of charge. So I've got a uniformly charged ring, and we'll say that it's got some charge Q. Let's say that it has a charge per length uniform lambda. And I want to calculate the field along the axis of the ring at some point P. And let's say that it's a distance of x meters from the ring. I know that if I break my ring into little elements of charge delta Q, I know that delta E, any piece of that ring will cause an electric field that I can write as 1 over 4 pi epsilon naught delta Q over R squared, where R, let's say, suppose we'll call that R from that point, and let's say that the ring has a radius of A. So R squared would be equal to A squared plus X squared. We can look at some symmetry here, though, to make this problem simpler before we even set up an integral. Notice that the electric field at any point on this ring has a component that goes in the direction of X. One of the components goes in the direction of X, and the other component is perpendicular to the X-axis. We can call that E perpendicular. The one that goes along the axis of X, of course, I can write as delta E cosine theta. But the E perpendicular one is kind of interesting because notice for every point up here, the perpendicular component of E will be canceled by the perpendicular component of E from a component of charge down here. Likewise here and here, here and here, here and here, all around. So E perpendicular is going to be 0 because for every one that points one way, you're going to get one that points the other way from the element of charge on the opposite end of the ring. So symmetry makes this problem quite a bit easier. What I can do then is say I can write this as delta E cosine theta. I can write this as delta Q divided by 4 pi epsilon naught. R squared I'm going to write as A squared plus X squared. Cosine theta, which is this angle here, I can write as cosine theta, I can write as X over R, or X over square root X squared plus A squared. That makes this X, that makes this X squared plus A squared to the 3/2. Now notice, this is going to be the one case where we don't have to change delta Q or dQ, because all I have to do is add up all of the charge around the ring, and that will give me the total charge. Notice, A is a constant, X is a constant, Q will be a constant if I add it up all around the ring. Therefore, I don't have to do an integral, and immediately I can say my electric field is just going to be equal to Q times X divided by 4 pi epsilon naught A squared plus X squared. I didn't have to change dQ to lambda dx, sigma dA, or rho dV. That's a very special, this is the only case I know of in electrostatics where you don't have to convert dQ to something else, but it works very nicely, and that is my electric field. Suppose X was equal to 0. Well, then E would be equal to 0 as well, right in the middle of that field, because EX would be 0 and E perpendicular would be 0. There's another calculation that sort of follows from this, and it's kind of a nice one. Imagine if you had a bunch of rings added together to form a disk. Now, this is a more complicated problem, but it's awfully fun to do, so let's do it. What we would do is take our answer for one ring and integrate over the entire radius of the disk by picturing the disk as being formed of a bunch of concentric rings. So here's my disk, and I have these concentric rings, like so. So, let's say we have a disk of radius capital R. It has a charge per area of sigma, it's uniform. And I want to calculate E along the axis of the disk at some distance x from the center of the disk. As I say, we consider the disk to be a series of concentric rings. We'll use the answer from this problem and integrate over the radius of the disk. So what do we have to do to make sure this works? First of all, if I have a ring of radius r that's less than a, so maybe a ring in here somewhere, suppose it's some little r, the area of that disk, that little disk, would be 2 pi r, the circumference of that ring, times the thickness of the ring dr. So this is the area of one ring. So I could write my electric field of one element as 1 over 4 pi epsilon naught. I'll use what I had from before. This would be x over x squared plus r squared, little r squared, because it depends on where I am in the ring, in the disk. To the 3/2 times the area element 2 pi r times sigma dr. And if I want to find the total electric field due to the disk, E is just going to be 1 over 4 pi epsilon naught times the integral from 0 to the entire radius of the disk, capital R, x over x squared plus little r squared to the 3/2. And up top we have a 2 pi sigma. I can pull that out of the integral. And I have an r dr. Interesting. I can pull this x out of the integral as well. It's a constant. Pull that outside, make it look better. This is what we call a u du integral. It's very simple to do because the derivative downstairs, 2r, is upstairs as long as I multiply by 2 on top and 2 on the bottom. That gives me sigma x on top. The pi's go away. The 2's go away because I multiplied a 2 on the bottom, so I've got 4 epsilon naught. Now I've got to integrate. This is integrating essentially du over u to the 3/2. So we let u equal x squared plus r squared. Du is equal to 2r dr. And notice we have an r up top, so I have to multiply a 2 on top, put another 2 on the bottom. That cancels that 2 in the numerator, so I end up with sigma x over 4 epsilon naught. That should be an integral. Integral of du over u to the 3/2 is u to the minus 1/2 times a minus 1/2. So what I get when it's all said and done, E is equal to minus x times sigma over 2 epsilon naught, 1 over the square root of x squared plus capital R squared minus 1 over x. Beautiful. Let's do something fun with this. Suppose, and that's the answer, that's the right answer, but suppose we have a situation where x is much, much greater than r. Let's do another trick. Let's expand the denominator of the second term, this term here, I should say, in a Taylor series. So let's expand x over square root x squared plus r squared in a Taylor series. I know that I can write the term 1 plus sigma to the 1/2 is approximately, 1 plus delta to 1 minus delta over 2 plus higher order terms. So in this case, what I'm going to do, I'm going to write this as x divided by the square root of 1 plus r squared over x squared, 1 over 1 plus r squared over x squared to the 1/2. And that's approximately 1 plus r squared over x squared, all to the minus 1/2. So what that gives me then is an electric field that's approximately, because it's an approximate answer for x much, much greater than r, I can write that as 2 pi over 4 pi epsilon naught times sigma, and that's going to be x over x minus 1 plus r squared over 2x squared, which is going to give me then, obviously x over x is 1, 1 minus 1 is 0, so this is going to make this really simple. It's going to look like sigma pi capital R squared over 4 pi epsilon naught x squared. Notice, that looks like a charge, and essentially what we have again is a point charge, because this is q essentially over 4 pi epsilon naught times the distance squared. So it looks like a point charge if we go far enough away from the disk. It's kind of a cute little addendum to this problem. I think we'll stop with this, and I'm going to start a new segment on the motion of charged particles in a uniform electric field. That will be the next and last topic for this unit. So we'll pick that up next time. Thank you.